Look, I'm just a geologist. I like rocks. I love rocks.
Why is today so important, Jesse? What anniversary do we have today?
Well, it's the 1 week anniversary of last week's podcast, of course.
Yeah, it is. That's most important.
That's what I was getting at.
I think this is the 40th anniversary today, this morning, of the eruption of Mount St. Helens, which was a notable event in our Earth.
Now, everybody raise your hand if you were alive when Mount St. Helens erupted. Oh, just Tim and I.
So 2 out of 4 here.
I was a wee lad of 1 year and 363 days old.
Before we started, I shared some pictures that I found. I guess we'll post them up on the old website.
Those are wild pictures.
Yeah, pretty cool.
So, we could put them. I could retweet that on the Twitter account.
Yeah, check the old.
What's our Twitter account, Chris?
It's at Geology Flannelcast.
Awesome.
Check us out. Follow us.
Yeah.
So Jesse, before we started, Jesse was showing this picture of a hiker up in the Cascades on, was it Mount Adams?
Mount Adams. Yeah, Mount Adams.
So hikers at the summit of Mount Adams, and this person's watching Mount St. Helens explode. And then in the second picture below it, you see him basically sitting on his butt. It knocked him on his butt. The shockwave coming from the explosion of the volcano. And
that is crazy.
Yeah, it's his picture. He's just I assume the hiker was okay, but
or at least his camera was.
Yeah, I mean,
and we're talking film, baby, film.
Yeah, Mount Adams is what, 25 miles or so.
Mm-hmm. So it's 25 miles away ish from the eruption of Mount St. Helens, and that shockwave is so strong that it knocked him on his butt. Like that's pretty impressive.
Yeah,
I forget where is I'm sorry, Mount Adams.
It's to the right. It's to the east.
To the right.
Right.
To the right. For those science people listening, it's to the east.
Because Mount St. Helens was north, like pretty darn close to north, right? And so that's a pretty impressive shockwave to be.
I assume in the shockwave now. The picture, back-to-back pictures, he's on his butt. So
the emotional stress of it all, I just fainted. And
maybe. I was just reading a story, and we'll obviously post the link again. It was I'll post the link. There's it's a good sort of pop sci article from Nat Geo, and it talks about, so if you ever look at the the volcanoes in the Cascades, they all basically run north to south. They're parallel basically with the coastline. So the thing that I never realized until I started reading this was that if you ever look at that, Mount St. Helens actually is offset from that chain of volcanoes. It if you look at say Mount Rainier and Mount Hood and Mount Adams, Mount St. Helens actually sits a little bit to the west. It's like an outlier. And so there was a lot of question of why A, it did that, and why B, it's volcanic if it's not sitting, in line with the other ones. Because if you're in line with the other ones, you're at, the plate subducting needs to get to a certain depth before you dewater and degas and heat up the overlying crust enough to melt.
Could it be that magma plume is just kind of following a path of least resistance that made it offset a little bit?
No. So
no.
So
do you have the answer why it's offset?
the current. So this is breaking today. This story came out, and they probably held it to do it on the 40th anniversary. I'm sure. Mm-hmm. It's the magma plume that basically feeds Mount Adams, because Mount Adams is basically due east of Mount St. Helens, where the other volcanoes, they're either north or south. And so it's the same magma plume, but there's a large batholith that formed. So there was like a slug. So a batholith is just magma that's cooled and hardened. And so this it's called the Spirit Lake. If you're familiar with the region, Spirit Lake up there, Spirit Lake batholith is this large, they think, basically slug of magma that started making its way up the plume that feeds Mount Adams, and it started solidifying, and it basically cut the plume in half. And so now some of the plume goes to the east and some of the plume goes to the west. So I guess technically a path of least resistance. Even though
So Chris was right.
I refuse to admit that.
So he ridiculed me, even though
I need to break you down before I build you back up.
Is that why the frequency of Mount St. Helens is so much greater than Adams?
Oh gosh, you're asking the good questions here. That is so far sort of unknown. That's the next thing to look at, is why Mount St. Helens seems to be a little bit more explosive and a little bit more frequent in terms of its eruption. There's some thought about that maybe the Spirit Lake batholith is sort of semi-solid,
angled in a way or something.
I'm not necessarily sure about angles. The team looking at it though, so one thing about it is, Mount St. Helens, because it's further to the west, the subducting plate is shallower. And so that was part of the question. If it's shallower, it shouldn't be hot enough to melt. The plate under Mount St. Helens is only 42 miles, where under Mount Adams it's 62 miles, which is the right depth. And so people are always like, oh, why, if it's not, if it's not that deep, it shouldn't be melting there. And so now that sort of explains that. The team looking at it right now has a great name. And so it's called I'm trying to find the name right now. It's the Mount St. Helens. Basically the acronym is IMUSH. It's magma under Mount St. Helens, IMUSH. Which I feel like half of doing research is coming up with sweet acronyms.
Yes,
absolutely.
So Jesse, we have a question from our Patreon real quick, if you wouldn't mind. Why did it erupt sideways?
That's not a question I'm equipped to answer right now. I'd have to look into it. That's a great question though.
So
well, I got the answer.
I was just going to say
everyone else does. I'm going to sign off. Forget.
I'm going to answer this, but Jesse's going to tell me I'm wrong until I finish, and then he's going to say, "Oh, I guess you're kind of right."
Pretty excited to do that, quite frankly.
Well, so what ended up happening was, as that magma was coming up, so you have Mount St. Helens is the magma plume underneath. That's like the fuel for the volcano. And it started pushing to one side a little bit. And, this magma, the magma is really hot. So the rock starts expanding. And so one side, because it was offset, it wasn't going completely right up the middle because it was offset. There was a bulge on, I believe it was the north face of St. Helens.
Yep. North side.
It was the north face. Yeah. And it just started to bulge out a little bit on that side. And the closer and the more we go towards the side, the more it started to bulge and bulge and bulge. And so as this magma plume's moving, it's setting off small earthquakes. I think like on an order of like a 4.0 or, stuff like that, maybe 5.0 earthquakes. And so what ended up happening was one of the earthquakes set off this giant landslide. Just because of that bulge sticking out, the ground was unstable. And the earthquake was kind of like the straw that broke the camel's back. And what ended up happening was it was the largest recorded landslide in human history, like ever recorded, of the north face of St. Helens literally falling off. And you can see there's YouTube videos of this. They've stitched
the time lapse is really cool.
Footage.
Yeah, the time lapse is just whoop, like the whole side of the mountain kind of falls down, and then the whole side of the mountain kind of explodes sideways.
Mm-hmm. And so what actually ends up happening is, a lot of people don't realize this, but inside magma, there's a lot of dissolved gases, right? So just think like you have like a bottle of Coke, right? And you shake this thing up, and then all of a sudden you twist the top off, And what happens? That bottle of Coke explodes, right? Because there's carbon dioxide dissolved in that bottle of soda, right? So let's go back to the magma. The magma's got all of this carbon dioxide dissolved in it, right? So now the largest landslide that humans have ever recorded happens, right? You take off a lot of weight, a lot of overburden. You essentially pop the top.
Cap out. Yeah.
Yeah. And now because there's no more pressure pushing down on that magma, all of the gases come out. It kind of fizzes out. And that's what actually caused that explosion coming out laterally. So it was a mix of, it was mostly just the landslide. The bulge was kind of coming off the side of the volcano. Earthquake caused a giant landslide. You take away all the pressure and boom, get this giant lateral blast.
Now, just imagine, like, if you're a scientist, you think, okay, the cap's coming off the top. This is what's going to happen. All these geologists think, okay, this is what's going to happen. And then out of nowhere, the cap, so to speak, is now on the side of the mountain that nobody was expecting. So instead of opening a soda from the top, you're opening the soda from the side, and it's kind of shot sideways.